Modern autonomous vehicle systems are often over-censored. For example, in the Argoverse 1.1 dataset, there are 7 full HD cameras, each recording at 30 frames per second, in addition to other LiDAR and stereo cameras. Processing this high-resolution data leads to high latency, which is very undesirable for the time-sensitive and safety-critical task of autonomous navigation. We have too much data and too little time to process it. The most effective solutions today are still naive downsampling and frame dropping. However, this is a blatant waste of the over-censored setup, so in our work, we improve on this. Inspired by the human fovea, our solution is to locally magnify the salient pixels of interest while performing the downsampling. This helps preserve the original information density in the salient image regions. In the figure shown here, whereas standard subsampling would lead to a uniform scale of 0.5, with non-uniform subsampling, we're able to achieve a local scale of 1.2 in the regions of the image that we care about, while maintaining the same canvas size. Let's look at previous work. There's a paper called Learning to Zoom that already suggests saliency-based image deformation for gaze estimation and fine-grained image classification. Would their pipeline, shown here, work equally well for our chosen task of object detection? Well, this was the first thing we tried, but as we quickly found, there are issues. One, we can't directly output detections from the warped image. Instead, we would need an inverse transform of sorts. An even deeper issue is that learning the saliency map as a function of the input image, as done in this paper, would require computing the rough location of each object in the scene, and thus is arguably as difficult as the task itself. So how does our pipeline work and address these issues? First, the salient image regions are computed using the locations of detections on the previous frame, which is a strong prior for object locations on the current frame. The warp is then guided by the saliency map, which is a heat map representation of this prior, constructed using Gaussian kernel density estimation on the set of centers of those previous detections. Then, to carry out the intelligent non-uniform subsampling, we adopt a spatial transformer formulation based on the one proposed in Learning to Zoom, but fine-tune this to our chosen task of object detection. Once we have the warped and downsampled image, we pass it through an object detector and inverse transform the resulting bounding boxes back to the original space. All components in our pipeline are differentiable, which allows us to optimize the system end-to-end. Here are key ideas and contributions. First, we use the simple but highly effective prior of previous detections. This serves as a computationally cheap but data-efficient alternative to learning the saliency map as a function of the input, as done in Learning to Zoom. Second, we devise an explicit backward label mapping and demonstrate that this function is identical to the coordinate transform used to warp the image in the first place. Third, we propose an elegant modification to the spatial transformer formulation that provably prevents cropping, which would otherwise lead to intolerable errors in the chosen task of object detection. And lastly, we separate the non-uniform subsampling along the x and y axes to ensure that bounding boxes remain axis aligned. This is a crucial geometric invariant for object detection. Our method improves the performance of faster RCNN on the Argoverse HD dataset at 0.5x resolution, both before and after fine-tuning. This increase in accuracy comes at the minimal cost of about 2 milliseconds of additional latency, suggesting that we've achieved a new optimum on the latency accuracy frontier. This is confirmed by our state-of-the-art performance on the streaming accuracy metric. FOVEA also generalizes well to multiple detectors, including RetinaNet and YellowF, and multiple AV datasets, including BDD 100K, boosting performance in all of these cases. Here are some qualitative examples of what FOVEA looks like in practice. Note the behavior of the detector at the horizon in the scene. Normal object detectors miss objects at 0.5x scale that they would otherwise pick up at 1x scale. Our method reconciles some of this difference.